fugitive tries to hop on a freight train traveling at a constant speed of 5 meters per second. Just as an empty boxcar passes him, the fugitive starts from rest and accelerates at 1.4 meters per second squared to his maximum speed of 6 meters per second, which he then maintains. How long does it take him to catch up to the empty boxcar? What is the distance traveled to reach the boxcar?
Perfect. Matt, I'm going to expect that voice to maintain through this entire video.
No problem.
What are we solving for here?
So it's in two parts. So we're solving for time for A, and we're solving for the distance traveled for B. And we're probably going to have to solve in that order to get each answer.
Let's talk about this a little bit. Our fugitive is catching up to this train. They're starting at the same place, and the train is going at a constant 5 meters per second. The fugitive starting from rest. So initially, that train is going to get a bit of a head start, but then the fugitive is going to start accelerating until he catches up to the train. So we want to solve for the amount of time it takes for the fugitive to catch the train. Let's start with that in part A. So I've put a little drawing here. Our train is starting. It has a constant velocity, meaning v initial and v final are equal, of 5 meters per second. We can also state, but we don't have to, that its acceleration is equal to 0 meters per second squared. Now we have our fugitive starting with 0 meters per second velocity and accelerating at 1.4 meters per second squared. They're both starting at the distance is equal to 0, time is equal to 0. Let's start with our fugitive. How long is it going to take for the fugitive to get from 0 meters per second all the way up to 6 meters per second?
We're solving for time.
We are.
Do we not know that yet?
We don't know how long it takes to go from 0 to 6 meters per second for the fugitive, but we can solve it.
Could we use v final equals v initial plus acceleration times time?
Yeah, let's try
for it?
that. V final equals v initial plus at. What's the final velocity that we're considering here?
The final would be 6 meters per second.
Nice. We have 6 equals the initial 0 plus the acceleration is what?
1.4 meters per second squared.
Nice. Go ahead and solve for that time. I'm going to call this time t1 because it's the amount of time he takes to get up to speed. So this is going to be 6 divided by 1.4.
And I got, is time 4.29 seconds?
Yeah, perfect. 4.29 seconds. Let's see how far he traveled in those 4.29 seconds. So now we have time, we have initial velocity, we know the acceleration. How can we calculate the fugitive's distance covered in that time?
So we know in 4.29 seconds, he is moving 1, and I forget the unit, but we know the train is moving at a rate of 5 meters per second.
Oh, so what you're saying is that now he's moving 1 meter per second faster than the train.
And that's how we'll know when he's caught up, is we have to know the train is going plus 5, plus 5, plus 5. And then he will accelerate to this rate of 6 to the point where he'll eventually catch up with them when we add this all together. So
exactly.
It's tricky, but yeah, it's not. Yes, it's tricky.
Good call. So what we're going to do first is we're going to make sure that he hasn't caught the train by the time he's accelerated to 6 meters per second. Now, we can mostly assume this to be the case, but let's just verify it using our methods. I'm going to use the second equation, delta x equals v naught t plus 1/2 a t1 squared. This is going to give us the distance that the fugitive travels while he's accelerating, or she. I don't want to make any assumptions here. Delta x, what's the initial velocity of the fugitive?
The initial velocity of the fugitive is 0.
0. What's our time?
4.29 seconds.
Right. Doesn't really matter for this part because it gets multiplied by 0 anyway. Plus the 1/2, 1.4, that's our acceleration, times 4.29 squared. Can you calculate the distance that the fugitive travels in this time? 0.5 times 1.4 times 4.29 squared is what I'm doing on my calculator.
I got 9.2.
I didn't get that. Could you tell me exactly what you typed in?
I put in 0.5 times. Oh, I typed it in wrong.
That's
I
okay,
put
that
in
happens.
I put in 1.0 instead of 1.4. I'll try that again.
Gotcha. This is why we check. A lot of times I'll be doing problems and I'll get something wrong, and it's always just the silliest mistake.
This time I got 12.89.
That's what I get. So, 12.89 meters. Let's just verify that he hasn't caught the train by calculating how far the train traveled in that same amount of time.
Okay.
So, this is delta x for the fugitive. We're gonna do delta x for the train. Matt, what equation should we use here? Or how should we fill in our second kinematic equation to solve for the train's distance?
So we have the distance that the fugitive traveled,
Right.
and we're trying to find how far the train traveled.
Yeah.
Is it possible to do this same equation again, but then plug in what we know about the train instead of the fugitive?
Yes. Go ahead and start that. Let me know what I should plug in for V naught, V initial.
Okay, so the V initial for the train doesn't start from rest.
Mhm.
The train starts at the constant speed of 5 meters per second.
Perfect. And how much time are we taking for this train? We're testing it over the same amount of time, right? To see how far it travels.
Okay, so we can put the same time that we had plugged in before.
Exactly.
That would be 4.29 seconds once more.
Plus 1/2. What is the acceleration of the train?
So the train's at a constant speed. It's not accelerating.
Yes, that's huge. So notice here, constant speed means acceleration is 0. That's a trick that they're going to throw into a lot of problems that not everybody sees their first time through.
And then we put in 4.29 again, squared.
Right. And really, this whole second half, we don't have to do any calculations because it just gets multiplied by 0.
Right.
Let me know how far the train travels, Matt.
Would that be 21.45 meters?
Yes. So, did they travel the same distance?
They did not.
Right. That's a good way to verify that we have to expand this problem a little bit. This is where it gets a little tricky. So, our fugitive, his total distance covered is going to be something like this. We know that from here to delta x, from starting to 6 meters per second, it's going to take him 4.29 seconds. So we have to get that the delta x of the fugitive is equal to the delta x of the train. What we're going to do for this is the delta x of our fugitive, it's going to be v initial t1 plus 1/2 a t1 squared. But then once he gets up to that speed, we're going to have a new initial velocity. We're going to call this v naught prime. And v naught prime is equal to 6 meters per second. Or in other words, it would be his v final from the previous one. And that is going to be multiplied by t2, some new time. All of this is going to be equal to the train, and the train's velocity is constant. V naught train, I guess I should call this v naught fugitive and v naught prime fugitive, times t1 plus v naught train times t2. This is pretty tricky. We can do this because this entire umbrella here falls under the distance traveled by the fugitive. First, whenever he's getting up to speed, and then when he's moving at constant speed. The second part is the train moving at constant speed for time t1, and then continue to move at that constant speed for time t2. So this falls under this umbrella of the distance traveled by the train. And we know they're going to be equal.
So this is my first exposure to V naught prime and these labels.
Yeah.
So I can't pretend that
It's tricky,
I fully
right?
understand it yet. This is my first exposure to it. Are these labels that we designate to help organize the problem? Or is this a whole new equation?
This is actually something kind of separate. You don't have to memorize these labels. This is something that I'm coming up with in order to give meaning to these variables. All I'm doing is I'm differentiating the initial V naught from the final V naught.
Oh, so this isn't a new equation. This is just something you're using to understand what each thing is when you're solving.
Exactly.
Okay.
And there are multiple ways to do this problem. I decided to put it into a giant equal equation here. We know that they have to travel the same distance. And so we know that the distance traveled by the fugitive is going to be the acceleration distance plus his constant velocity distance whenever his velocity is 6 meters per second. For the train, it's going to be the constant velocity for time t1 plus the constant velocity for time t2. So it turns out what we're solving for here is just t2. This is going to make more sense. Let's continue with the process. So the initial velocity of our fugitive is 0 when they start. T1 is 4.29 plus 1/2, 1.4 times 4.29 squared. We already kind of did that, so we know that this part's going to be 12.89 meters, right? This is what we did in part 1 here. Now, we have to add 6 meters per second, because that is the velocity that he gets up to, times t2. And t2 is what we're going to be solving for here. This is going to be equal to the velocity of the train, which is 5 meters per second, times t1, which is 4.29, plus the same constant velocity of the train, times t2. Now, this is a lot to look at. Immediately, I'm going to simplify it. We know that this whole section is equal to 12.89, because we solved that earlier up here, plus 6t2 equals, what was 5 times 4.29? We solved that before, right?
Oh, that is 21.45.
Plus 5t2. This is solvable, isn't it?
It is.
I'm going to start by subtracting 5t2 from both sides, and I'll subtract 12.89 from both sides. Okay, 6t2 minus 5t2. What is that going to be equal to?
1t.
Yeah, or just t2.
There we go.
6 minus
so
5
it
is 1.
isolated it.
Yeah, we did. And this actually worked out really nicely. We don't have to do any division after this. Pull out your calculator and go ahead and do 21.45 minus 12.89. Keep in mind, these just cancel out. That's the whole point of subtracting those numbers.
8.56.
Perfect, that's what I get. 8.56. What's the unit?
8.56 meters.
It's time.
Oh, it is time. Okay. Seconds.
Seconds, there we go. Now, is this the total amount of time that it takes the fugitive to catch the train?
No.
How do we get the total amount of time?
Isn't this time just the time it took to get to the rate of 6 meters per second?
No, that was T1.
Oh, that was T1. Okay.
This is the time it takes from whenever the fugitive gets to 6 meters per second to then catching the train.
Okay.
So we can add them together. I'm going to put this in a circle because it's not the final answer. So our total time, I'll just call it T, is equal to T1 plus T2. So we have it being 4.
Oh, so T1 was 4.9.
Yeah, exactly.
Okay, so we have that.
Go ahead and calculate the total time.
That would be 12.85 seconds.
Nice. Awesome. Is this making sense?
This was one of the hardest ones, I
Yeah,
think.
not an easy question at all.
Yeah.
So, if anyone is watching this, this is not the only way that you can solve this problem. Let us know if there's another way that you could figure out how to solve this, and maybe if you can solve it easier or faster. And also, make sure to remember this kind of math next time you're trying to hop onto a moving train.
Oh, brother, where art thou?